The extreme heat is back.
Temperatures are going to be running about 12 degrees above normal.
The heat can be deadly.
In Phoenix, Arizona, residents are already experiencing what life must feel like on a hot planet. In the record year 2020, temperatures were over 43 degrees Celsius for 50 days in a row. That's when airplanes even have trouble taking off, because hot air is thinner, so there's less lift beneath their wings. Without air conditioning, the heat becomes unbearable.
In the summertime, the peak temperatures during the day have been increasing by maybe 1 to 2 or even 3 degrees Fahrenheit, so maybe 1 or 2 Celsius. Whereas the nighttime minimum temperatures have increased by 9 degrees Fahrenheit, or 5 degrees Celsius. So very substantial warming at night, much more so than during the day. And so much of that is caused by local phenomenon and the urban heat island effect.
A typical problem in cities when it's hot. At night, the surfaces of buildings and streets radiate the heat absorbed during the day, and cooling no longer takes place. It's a massive strain on the inhabitants.
Here in Phoenix, we've been having over 150 heat-related deaths every year in the recent past.
Around the world, cities are having to prepare for a hotter climate. Even in the next few years, average temperatures could rise significantly. In Cape Town, South Africa, by 2 degrees Celsius. In Sydney, Australia, by 2.1 degrees. In Rio de Janeiro, Brazil, by 2.2 degrees. In Shenzhen, in southern China, by 2.3. And in Geneva, Europe, by even 2.5 degrees Celsius.
What's crucial is the speed at which the temperature changes, because that determines whether and how quickly we can adapt.
Extreme heat has always existed in the history of the Earth, also as a long drawn-out climate phase. For example, 56 million years ago. In the PETM, the Paleocene-Eocene thermal maximum, the Earth became 5 degrees hotter in only 10,000 years. In terms of Earth's history, that is extremely fast, and it enables us to draw conclusions about today's even more rapid rise in temperature. At that time, volcanic eruptions ejected carbon dioxide into the atmosphere, and the planet heated up. Blooming landscapes with rich vegetation were transformed into savannas. Numerous traces of this can be found today in the Bighorn Basin in the state of Wyoming, USA. Paleontologist Philip Gingrich comes here every year to track down fossils from this hothouse period. He's interested in the fossilized remains of mammals that lived here at that time and adapted to the hothouse climate. He compares these finds with those dating from before and after the PETM. According to Philip Gingrich's research, 56 million years ago, some animal species became 20% smaller in size.
So these are adults. Oddly, the one in the middle is smaller.
The smaller bone of a prehistoric horse also dates from the PETM.
I suppose that the change in climate, the change in vegetation is the reason for these animals getting smaller.
To survive, animals adapted through dwarfing within 10,000 years. We don't have that much time today.
We have a very good record of our emission of carbon to the atmosphere since the 1950s, year by year by year by year by year. And if that continues at the present increasing rate, we will reach a PETM hothouse Earth in about 200 years. That's about 6 or 7 human generations. That's not very long.
It's a challenge for humanity. Around 8 billion people live on the planet today, more than half of them in cities. Rising temperatures there are an increasing problem. Cities like Phoenix can be up to 10 degrees hotter than their surrounding regions. To combat solar radiation and keep the heat down, areas of shade are being created in the U.S. metropolis, with more to follow. City planner Ariane Middle and student Florian Schneider from Arizona State University are developing special software for this. It calculates how far additional shade can sustainably reduce heat in the city.
The way we design neighborhoods really impacts how we experience the heat, the type of materials that we use, the way we arrange our buildings and our trees. And MARDI, this instrument here, can measure the heat that you experience when you're outdoors. In hot areas such as Phoenix, the main driver of how you experience the heat is actually the radiation. So that's the shortwave and longwave radiation that hits your body, the heat load that your body experiences.
MARDI measures the direct and indirect heat radiation. It's also present in the shade.
We took MARDI out on a road trip to look at different types of shade and measure the mean radiant temperature under different types of shade to see which shade type is most effective in keeping people cool during the summer.
The cooling effect of shade varies greatly. Under trees, it depends not only on the density of the foliage, the plants also evaporate water, which has an additional cooling effect. Shade under protective roofs is less effective, but many cities are experimenting with these wherever space for trees is lacking. MARDI provides a complete data set for the first time, enabling the different types of shade to be utilized strategically in other cities. A further measure is light-colored asphalt, which is already being used in some cities to reduce the heat. Its surface reflects the sunlight, preventing the asphalt from heating up and radiating heat at night. However, it's not a cure-all. Researchers measured its effect as part of an experiment in 8 different neighborhoods in Phoenix. During the daytime, the radiated heat makes people uncomfortable. Although it radiates up to 3 degrees less at night, it does not cool the air sustainably. The research also shows that the heat in Phoenix is unevenly distributed across the city's neighborhoods. Satellite and thermal imaging data reveal that some areas are 2 to 3 degrees Celsius hotter than others.
When I was first starting in this field, there was really an emphasis on just cooling cities broadly. But now we're starting to recognize that we can be more strategic with our cooling initiatives and focus on those living in parts of the cities that are the hottest, but also the most vulnerable.
Temperatures are especially high at this bus stop. The wide streets and adjacent buildings absorb a particularly large amount of heat during the day and store it. To test new heat-dissipating materials integrated into the roof of the bus stop, David Saylor comes here regularly with his thermal imaging camera. The new roof panels really do remain much cooler than their surroundings, even in direct sunshine at 43 degrees. The new materials come from freezer research. They could only be really effective against the heat if they were used on a large scale on rooftops and facades. These and other measures are sorely needed. Heat-related deaths in Phoenix have now risen to over 300 per year.
So the magnitude of the adverse health effects are quite large. And in countries like Germany or in many more temperate climates, we still have to be very concerned about heat because the planet is warming. And especially in locations that don't have a lot of access to air conditioning and don't have a population that's not acclimatized to extreme heat, those populations are particularly at risk.
The dilemma is that the air conditioners guzzle energy and thus contribute to global CO2 emissions. So, if there are more of them due to it getting hotter and hotter, the greenhouse effect will intensify accordingly. Berlin, Germany, is an example of how much the situation in the temperate climate zones has already changed. Since the 1960s, Berlin has been steadily heating up. Its climate increasingly resembles that of cities further south. Compared to 1960 in climatic terms, the capital is at the level of Heilbronn today, and by the end of the century, according to calculations by climatologists from Lausanne, it will be at the level of northern Spain. Since 2019, to stabilize its climate, Berlin has been relying on a plan to preserve and expand its green areas. But under growing pressure from construction, these valuable areas are in danger of being lost. The situation in New York is even less favorable, despite Central Park and some green skyscrapers. Indeed, measures such as greening, new materials, and additional shade are only helpful locally. With the predicted rise in heat of 3 degrees by the end of the century, they won't be enough. In other regions, the effects of the new hothouse period could be truly dramatic. Some parts of Central and South America could become uninhabitable, as well as some regions in Africa where the deserts are growing and becoming even hotter. About 3 billion people are affected. It will also be difficult in coastal regions where warmer oceans are already releasing large amounts of moisture into the air. This is a problem for the megacities of Southeast Asia and India in particular. Mumbai, for instance, on the Arabian Sea. The sweltering heat in the city is making life increasingly stressful for its millions of inhabitants. The combination of high temperatures and more than 70% humidity moving from the sea into the city poses an extreme strain on the human body. This heat is prevalent not only in the city, but also along the entire west coast and further inland, everywhere that is hot and humid. In such conditions, at temperatures above 35 degrees Celsius, heat exchange gradually becomes impossible for the human body. Organs begin to fail. Today, measuring stations in Dharavi, the largest slum in Mumbai, have detected critical climate values on 47 days a year. The fear is that the figure will rise to 261 days by the end of the century. But the humidity is not the only danger threatening life in the city. Before the end of this century, some parts of India's west coast could be flooded by the sea. This is because the sea levels are rising worldwide due to the melting ice masses at the poles and in the mountains. The Rhone Glacier in Switzerland's Valais region, for example, is in retreat. It's one of around 214,000 mountain glaciers on our planet, and its ice sheet is currently shrinking by 6 to 8 meters per year. The meltwater created the glacial lake in 2007. By the end of the century, only a few remnants of ice will be left, and the glacier will cease to be a water reservoir. A problem for around 10 million people in Switzerland, Italy, and France, whom the glacier currently still supplies with drinking water. The glaciers are melting so quickly because the temperature increase in the mountains is 2 to 3 times higher than the global average. That also explains why mountain glaciers are currently contributing around 21% to the sea level rise. A further 35% of the increase is due to melting ice at the poles and in Greenland. And the expansion of the oceans themselves as a result of warming accounts for up to 40% of today's sea level rise.
The sea level rise is the giant issue, especially because we're seeing so much evidence of really breathtaking changes in Greenland and also in parts of Antarctica. And these changes have the potential to produce not just 1, 2, or 3 feet of sea level rise, but, possibly tens of feet of sea level rise.
A look at Earth's history reveals just how quickly Antarctica could lose its ice and sea levels could rise. The Antarctic ice has nearly disappeared several times already. Clues here are provided by icebergs. As they melt, they lose trapped rock along the way that is deposited on the seafloor. Normally, it does not occur there. The rock forms part of core samples taken from the Antarctic seabed. The material proves to the researchers, led by geologist Maureen Ramo, that the ice sheets were smaller in the distant past, and that the sea level was therefore higher.
One of the periods that we're really interested in was 125,000 years ago. And we know that the Earth was about 1 to 2 degrees Celsius warmer than pre-industrial, which is about where we are right now.
The research group in the Bahamas can determine exactly how high the sea level rose at that time. Initially, there is talk of 8 to 9 meters. After further research and age determination of corals and other data from Earth's history, the scientists now arrive at just under half that figure.
Our revised analysis may have been such that the real sea level change, due to melting of ice sheets, was only about 4 meters. However, 4 meters of sea level rise is still devastating when you think about the current distribution of populations on the planet today.
A 4-meter rise in sea level would mean that major cities like New York would be underwater. No one likes to make predictions about when exactly that might happen.
According to our calculations, there are globally about 1 million people per centimeter of sea level rise that could be affected. So the accuracy of our elevation data, the accuracy of the maps we use to show flood risk and where people live really matter in understanding this risk, not just globally, but in any city, in any place that's affected.
Currently, Benjamin Strauss of the research organization Climate Central is expecting a rise of about 1 meter by the end of the century. Back in 2012, he already startled the responsible U.S. Senate committee with this prospect.
Dr. Strauss.
In the long term, we are likely to see many feet of sea level rise and be forced to redraw the map of the United States.
What you're saying is, get ready, you're going to see a lot more of this, and it's going
People
to
living in many coastal areas would have to get to safety, also in Europe.
Sea level serving as a launch pad.
The Netherlands and Belgium, northern Germany, and parts of Denmark are really the lowest and most vulnerable parts of Europe, but there are also many coastal defenses. So that's the hope that we'll be able to defend, at least during the course of this century, the sea level rise that we're likely to see. Another very vulnerable part of greater Europe is the UK. It's actually the #1 most vulnerable country in Europe if you measure by kind of total number of people living in areas likely to be below flood levels, coastal flood levels, this century.
Flooding and storms would impact a region covering 4,000 square kilometers, all the way to the university city of Cambridge, and also sections of Germany's North Sea coast. So far, the sea level rise in the North Sea has only been around 19 centimeters. Dams such as the one here on Norderney have so far provided good protection against this rise, and even now they're designed to withstand a further increase. But the protective structures themselves could also become a problem.
Moving to the US, one of the things we saw in Katrina was when you live inside a bowl, if the defenses fail, then the results can be catastrophic.
In the U.S. state of Louisiana, Hurricane Katrina devastated New Orleans on August 29, 2005, claiming 1,836 lives. Extreme events like this are making coastal planners rethink their approach.
I do think Louisiana is one of the most vulnerable places in the United States because it's losing its protective wetlands at such a rapid rate. They are sinking as the sea level is also rising.
The wetlands along the coast of Louisiana are sinking because ever since the Mississippi was straightened out and dammed, it has been unable to deposit any more sediment.
Most people have concluded, and I think rightfully, that it was a man-made disaster. Most people feel like, obviously, Katrina was a natural event, maybe exacerbated by climate change, but basically was a natural event. But the levees failed catastrophically, and that's what caused most of the damage, caused most of the mortality.
For John Lopez, Katrina changed everything.
In 2005, with Hurricane Katrina, we lost our house entirely. You know, we lived outside the protection system. We live on the shore of Lake Pontchartrain, and the house was gone.
John Lopez saw the disaster coming. Back then, he was working with the Corps of Engineers, the agency responsible for coastal and flood defenses, and had developed a kind of master plan for saving the coast. But before Katrina, nobody listened to him.
When I worked at the Corps of Engineers, I worked in their coastal branch, and what became really obvious to everyone, but it was just kind of accepted, was that coastal restoration was handled by one group of people and flood protection by another group. And they didn't hardly even talk to each other. And everything else was siloed.
It was the same situation when a navigation channel was built that ended up driving the floodwater from Katrina into the city.
While they were building the levees in the 60s, they, in a separate branch of the Corps of Engineers, created what's called the Mississippi River Gulf Outlet, a huge navigation channel that comes right into the heart of the city. So you had one branch of the Corps of Engineers making the problem worse, while another branch was trying to begin to make it better.
After Katrina, John Lopez was finally able to implement his plan. New levees are being built and connected to existing flood defense structures. The omnipresent erosion is being countered by plantings. However, the plan also provides for some strips of coastline to be abandoned to the rising seawater because they cannot be retained in the long term.
What actually cannot be prevented is that we have to give up territory. Now, if you told the U.S. that it had to give up 10% of its land, that would be problematic. But what we're saying very confidently is that the U.S. will lose 10% of its land to sea level rise if we don't comply with the Paris Climate Agreement.
To prevent any flooding right now, pumps are in operation around the clock. The Louisiana coast is an example of how climate change is exacerbating man-made mistakes.
There are a lot of serious impacts in the near term, and then at the same time, the choices we make. Do we limit warming to 1.5 degrees Celsius, or do we head to 3 degrees Celsius, business as usual right now? That's the difference between certain nations, certain great cities surviving or not surviving in the long run. It's the legacy that we set.
Many of today's coastal cities are already preparing for the inevitable rise in sea levels. Manhattan, which has so far been protected from floods by thick plastic barriers, is planning the Big U, a kind of dam that is meant to encircle the island by 2020. But political discussions have delayed its construction to this day. Technology is not only being relied on in the US, but in Europe too. The lagoon city of Venice, increasingly plagued by floods, has acquired the Mose protection system, planned in the 1980s. The barrier is still helpful during storms, but was not designed for the sea level rise of 60 centimeters expected in the Adriatic by the end of the century. It would have to remain closed permanently to prevent flooding, and during storms, it would be of little use to the city. Rotterdam in the Netherlands has planned for far higher sea levels in the future. The 22-meter-high gates of the lock facility in front of the city can hold off 3-meter waves and are designed for a sea level rise of up to 85 centimeters. But coastal protection is expensive. Many countries, just cannot afford it. Mumbai, India, for example, like many regions of the world, has taken hardly any precautions to keep the floods at bay. Yet strategies are needed for these areas too, because in the future, coastal habitats will undergo massive changes or disappear altogether.
Rising sea levels are a very long-term problem. Just as we remember the Greeks as the ones who brought us democracy, 2,000 years from now, people will remember us as the ones who caused sea levels to rise. For centuries and over millennia in the future, sea levels will continue to rise because we have increased the temperature of the planet.
Climate change goes hand in hand with a further major problem. Can the still growing world population be fed in the future? 3 types of cereals are now the staple food for 8 billion people, but their cultivation is becoming increasingly problematic. Wheat, with a good 220 million hectares under cultivation worldwide, suffers especially from periods of drought and heat. Each additional degree leads to a loss of around 6% of the harvest. In the case of rice, with 163 million hectares under cultivation, agricultural experts expect a 40% decline in harvests by the end of the century, and a 26% loss in the global corn harvest. The world's largest corn producer is the U.S. The state of Missouri is among the top 10. For several years now, extreme weather with droughts, heavy rain, and floods has been a constant threat to farmers.
When I was a boy, weather was more predictable. We had warm summers, but there would be a frontal passage, and normally rain would come, and normally it would be about an inch of rain. And Dad would say, that's a good rain, a good inch, that's just what we needed. But these days, instead of getting an inch of rain, we may not get any rain. And then when we do get rain, we get 2, 3, 4, 5, 6 inches of rain before the storm subsides. And I never saw that in my childhood, ever. Come on, Obi, let's get something. Mr. Gray! Mr. Gray!
Richard Oswald lives as a farmer in Langdon, Missouri.
Mr. Gray! There he is. Here, Obi.
Only his 2 cats, Sheila and Mr. Gray, now live in his former farmhouse. In 2019, they survived a month-long flood that put the entire region underwater. The second such flood in not even a decade. Sudden heavy rain, snowmelt farther north, and failed levees combined to make many homes uninhabitable, including that of the Oswald family.
This is the breakfast porch that my folks put on. That's where my parents ate breakfast every morning when I was a kid. This is about where the water level was in the house. The water was in the house for several weeks, and so that's really what did the most damage.
Richard has to give up the house.
It's a painful thing for me. It ties me to my family, to my parents, and to my children. My entire life experience is centered around that house and this land that I'm standing on now. And so it's difficult decisions to make.
Despite everything, Richard has remained a farmer and adapted his farming methods to the weather conditions. To avoid erosion, he grows soybeans and corn using the zero-tillage method. After harvesting, he does not plow the soil, but spreads the seed on the uncultivated field. So even during heavy rains, the soil is not washed away.
I think agriculture needs to adapt, and we have adapted. I started no-tilling in 1986. I experimented with no-tilling, not tilling the soil. And tillage here is still very much a part of the farm culture for many people. But I've also noticed that some people have adapted no-till into their farming operations slowly. and doing the things that we've been doing for quite a while, because they may not believe in climate change. They may not believe that they can have an effect on climate change, but what they do know is that when it rains like it rains and doesn't rain like it doesn't rain, then no-till is good. So I think people are adapting to it, maybe not because they believe it's going to help climate change so much as it just helps them do their job.
The weather has always been a risk for farmers, but the sudden extreme weather events are a serious cause for concern, and not just in Missouri. Richard has built his new house on a hill, but that kind of simple solution is not always available.
For ordinary people, the scientific predictions about all of these things now have a certain reality or a certain resonance that perhaps they didn't have before.
India fearing dozens of people are dead after part of a Himalayan glacier collapsed.
Die Fluten bringen Tod, Chaos, Zerstörung. Viele Menschen werden noch vermisst. Ganze Landstriche sind verwüstet.
More than 100 people have been killed after torrential monsoon rains triggered landslides and flooding.
Landslide in Himachal Pradesh that's killed 9 people. We understand it sent huge boulders tumbling down a hillside. One of them hit the bridge. It caused the bridge to collapse.
The Dixie Fire in Plumas County has become a worst-case scenario.
Oh my God! Yo! Oh, that roof is coming. Holy shit!
Hurricane winds reach 240 kilometers an hour.
This is a major storm.
It is one of the most powerful storms to ever hit the U.S.
Dutzende Tornados im Südosten und im Zentrum der USA haben Tod und Verwüstung hinterlassen.
The scientific evidence isn't just about the fact of how much the planet has warmed up. It's also about the impact of that warming. These are very damaging things. And, you know, I think one of the things that we saw clearly this year was that we can't just adapt. If your house burns down, that's a permanent loss. You don't just adapt to that. You live with that loss for the rest of your life. Or if people are killed in massive floods, those people aren't adapting. Those people are gone. Those people are dead. So the idea that we can just adapt is a kind of denial.
In agriculture worldwide, climate change has long been a reality. There is now an increasingly urgent discussion about what farmers will need to prepare for in the coming hothouse period.
Generally, you can say that regions that are already very dry will be affected by more periods of drought in the future. And regions where there's already more precipitation will also experience heavier precipitation. So that means that regions that are already having to deal with climate change will also have to deal increasingly with extreme weather events.
Heat and extreme weather are shifting vegetation zones in which crops can be grown, northward and southward respectively. In Africa, and especially in parts of South and Central America, farmers' yields have already fallen dramatically due to persistent droughts. The rise in CO2 is also giving grounds for hope, however. Carbon dioxide acts like a fertilizer for plants and could therefore compensate for the losses. But when they examine fossils from the Bighorn Basin in Wyoming more closely, paleontologists make a disturbing discovery. They find fossilized leaves from the PETM, the extreme hothouse period 56 million years ago. Insects have left feeding traces on them, and clearly more so than in the periods before and after the hot spell.
What I did was come to the Bighorn Basin and look at fossil leaves from before the PETM, during the PETM, and after the PETM. And during the PETM, the leaf feeding is absolutely unique.
Maybe there were simply more insects around at that time, but another explanation is also conceivable.
As CO2 goes up, plants become less nutritious. They have more carbon in their tissues and less nitrogen. And nitrogen is super, super important for animals. We make enzymes and proteins and DNA out of it. So if there's not as much nitrogen in the leaf, then the insect would need to eat more of the leaf in order to fulfill its needs.
Plants do indeed grow faster and taller due to increased carbon dioxide. But if they accumulate fewer nutrients in the process, that has a huge impact. And not just for insects. All living creatures that feed on plants are affected. And that includes humans. Around 80% of our food comes from plants. Lower nutrient content thus has a direct impact on agriculture and on feeding the world's population, which will continue to increase. In Leihgestern, in Hesse, Germany, a research project has been underway since 1998 in the grassland that is typical of the region. In heated experimental rings, the researchers expose the plants to CO2, simulating a climate that might exist a few decades from now.
Wir können also jetzt schon sehen,
we can already see how this grassland ecosystem will react to the changing climate that we expect in about 20 or 30 years.
Das heißt, also diese Daten, die wir jetzt erheben,
So the data we're collecting now is actually from the future. And it can help us to develop scenarios for the present and help us to react.
entwickeln, wie wir dann darauf reagieren können.
Within the experimental rings, the plants grow faster. Does this also apply to their roots, though? And are they getting more nutrients from the soil? The result is sobering, and it confirms the findings from Earth's history. Even with increased root growth, CO2 plants do not form more proteins. One possible reason is that the soil contains only a limited amount of nitrogen, which the plants need for protein formation.
Das hat auch Auswirkungen auf die Futterqualität.
This also impacts the feed quality. If less nitrogen is available for plant growth, then the protein content of the plants is also reduced. And that means that the cows that eat this green fodder have less energy available for lactation, for milk production.
Für die Laktation, für die Milchproduktion zur Verfügung steht und die Milchleistung
So with the same intake of fodder, the milk yield will decrease.
des Futters eben sinken wird.
What applies to animal feed also applies to our plant foods. A lack of nitrogen and therefore protein not only impacts the energy balance. Without sufficient proteins, plants such as rice can no longer absorb and store the elements iron and zinc either. These building blocks, which are vital for us, will then be missing from our plant foods. The quality of wheat will also decline under increased CO2 intake because it will contain less calcium, iron, and essential fatty acids. In addition, wheat will then form less gluten, which is necessary for baking bread. For plant ecologists, another hope has been eliminated.
Das war so diese Anfangsidee.
The initial idea was that the plants would absorb more CO2 and store it in the soil, where it would remain. We've now discovered that this doesn't happen. Quite the opposite, in fact. Feedback effects have taken place.
With increased CO2 output, the plants do absorb more CO2, but they release some of it again via their leaves and roots. The hotter it gets in the heated test rings, the more they do this. These plants no longer function as so-called CO2 sinks. The researchers also established that additional climate gases are emanating from the soil and fueling the greenhouse effect even more.
Wir haben bei uns festgestellt über diese
Over this 22-year period, we've noticed that nitrous oxide emissions have almost doubled. We've been confronted here by something we didn't expect at all. Truth be told, we were expecting quite the opposite.
Genau das Gegenteil.
The researchers discovered that in the rhizosphere, that is, the surrounding soil, the roots of CO2-fertilized plants trigger reactions among the organisms that settle there.
There's a whole bunch of bacteria and fungi in the soil, producing climate-relevant traces of gases, and some of them are even being activated by these gases.
The increase in CO2 in the atmosphere leads to the escape of far more dangerous climate gases, such as nitrous oxide and methane, that further intensify the greenhouse effect. If we don't significantly reduce carbon dioxide emissions, the temperature will probably be 3 degrees hotter by the end of this century than it was at the beginning of industrialization. But reduction alone won't be enough. New technologies need to be developed that can remove the climate gas from the atmosphere. At the Salk Institute for Biological Studies in La Jolla, California, molecular biologist Wolfgang Busch is working on plants that will not only provide food, but also remove significantly more CO2 from the atmosphere than before. As a so-called negative emission technology, however, the idea only works if the plants can also bind the CO2 for a longer period of time, with the help of a substance that plants produce at their roots, so-called suberin.
All wine drinkers are pretty familiar with suberin because it's the component that corks are made of. It's impermeable to water and doesn't let air in or out. And suberin is very interesting because it stores a lot of carbon that remains in the soil for a long time.
The idea is that suberin will keep the carbon in the soil for at least 40 years. Using classical cultivation methods and also with the help of genetic engineering, so-called genetic scissors, for instance, the plants are to be modified so that they can store as much carbon as possible via suberin.
These genetic scissors don't do much that's different. It's only about making precise changes to genes that we know can affect suberin, roots, and root mass. So in that regard, within 1 or 2 years, this kind of gene editing can very quickly result in plant varieties that are interesting for farmers.
Only plants with strong root growth are suitable. The deeper the roots drive into the soil, the longer the suberin and the carbon will remain bound there.
These ones all the way out to the side as well.
Today, the researchers are already speculating that if this technology were to work on a large scale, farmers might be able to sell rights for their negative emissions in addition to their crop yield. Work has already begun on initial field trials using soy, corn, and rice plants. However, only huge areas under cultivation can have a real impact on negative carbon dioxide emissions. The suberin plants would have to be cultivated worldwide.
Personally, I think we don't have time. The faster we are, the better. We have to remember that every second we're talking right now, incredible amounts of CO2 are being emitted and dumped into the atmosphere, which serves as a sewage treatment plant, so to speak, for our carbon combustion. And every minute we don't counteract, that is a minute lost.
To achieve the climate targets, further technologies for so-called negative emissions are being researched.
We've been working on climate change and what its impact will be for 10 to 15 years and have only actually warned people so far, rather than offering any solutions. And I personally don't regard that as enough. At some stage, it's just not enough. We know full well that change is taking place. What can we do to counteract it?
Take the oceans, for example. Throughout Earth's history, they have always regulated the climate as gigantic heat and carbon reservoirs. But with increasing CO2, the question arises as to when the system will reach its limits.
We humans put additional CO2 into the atmosphere by burning coal, oil, and gas. Half of it stays in the atmosphere and warms our planet through the greenhouse effect. The other half, a little less than half, is dissolved in the ocean, where it produces carbonic acid.
Can the oceans absorb even more CO2 than they already have so far? On Gran Canaria, ocean researchers from Geomar Kiel are working on this. To increase the absorption capacity of the sea, the CO2 stored as carbonic acid needs to be bound and thus neutralized. In an experiment with mesocosms, plastic containers filled with seawater, they have set a chemical weathering process in motion for this purpose.
Rock weathering is a process that takes place naturally all the time. Rock on land reacts with CO2 and water and releases minerals. These are then ultimately carried into the oceans via the rivers. And the CO2 that is bound via this reaction is then permanently stored in the ocean in the long term.
In the experiment, a carbonate solution triggers the weathering process. Carbonates occur naturally in many minerals and react with carbonic acid. When the solution is fed into the mesocosms, the carbonate reacts with the carbonic acid and binds with the carbon it contains.
The question is, can we accelerate this weathering process so that more CO2 gets bound in the ocean?
The deacidified seawater could then bind more carbon again. An impressive process, but a gigantic undertaking when extrapolated to the world's oceans. Moreover, it's still impossible to predict what it will mean to artificially trigger this weathering process on a large scale. Everything is still an experiment.
Preferably, we'd like to give nature time to be able to heal itself. But due to the speed with which we're intervening in the system, nature won't be able to deal with it naturally. So we may have to give it a helping hand here and there.
Every 2 days, the research groups take samples early in the morning for analysis in the laboratory later on. First, they want to study the processes in the mesocosms very closely. It's the first experiment of this kind anywhere in the world.
We just put our baby in the water. It joins us on all our trips. It measures the heartbeat of our mesocosms. There are 6 parameters we can measure with it: salinity, temperature, light, acidity, oxygen, and fluorescence. And then we can see whether things are going according to plan. And that's sort of the first indicator.
According to the research group's calculations, the process could remove up to 5 gigatons, that is, 5 billion tons of CO2 from the atmosphere. But that would mean adding around 8 billion tons of minerals to the oceans, an amount roughly equivalent to annual coal production. At present, the scientists are still investigating whether their experiment will have any impact on life in the oceans. The data look promising. The carbonate solution did not harm the microorganisms in the experiment.
Regarding the measures for active absorption of CO2 via any artificial or natural processes, we still have about 10 years before we have to make any decisions there. But we have no time left at all to reduce CO2 emissions. That has to start right now if we want to achieve the climate goals of Paris.
The climate catastrophes of the past few years have revealed the potential destructiveness of the new hothouse period.
Extreme weather events are playing havoc with our economic system and our social system. The big question, at what point do they occur so frequently that we don't have time to clean up the last one before we're hit by the next one?
A look back at Earth's history gives an idea of what is in store for us in the new hothouse period. We're going to have to work hard to see the connections more clearly and develop effective adaptation strategies.
We are actually in a completely new age. We are now the driving force in the climate system, and we have the greatest impact on the climate system, but also the greatest responsibility.
Research can only provide indications. We're the ones who have to act.
What's good for the planet is good for us. And I have to say, I don't consider myself a conventionally religious person, but if there is anything that would make me believe that there is a God who designed this, that fact, that what's good for us is good for the planet and vice versa, does kind of make you think maybe it was possibly designed that way.